Hello? Good evening, all. Eric, Howard.
Howdy, everybody.
Good evening.
Good evening.
Everybody have a good week, or 2 weeks, or whatever since it's been.
Nah, working all the time.
No, suck, Ken. Like we gotta get with these. We gotta get with the program, like all these retired guys here.
That's what I'm planning on doing. and then
Yeah,
I'm gonna disappear.
But the question is, when are you gonna retire? Right?
Less than a year.
Less than a year?
Yeah.
Good for you.
Yeah.
Good for you.
Mr. Peter.
Do you have something else lined up? Like as a part-time thing, or you just cold turkey and that's it?
It'll probably be cold turkey in the beginning. It'll probably go part-time, something else. And we're seriously thinking about living off the grid.
Oh, cool.
I'm considering it. Hey, Peter, you better restart because you got Mickey Mouse voice.
What, Wayne? Wayne? Can't hear me.
How's that?
Yeah, I can hear you. Just
Yeah,
had the microphone off.
Which signal generator did you use? Your own or the PARC one?
My own.
Okay. I couldn't get mine to work properly. Anyway, okay, that's fine.
What you SigGen?
Signal generator.
What, the PARC one?
Well, yeah,
Yeah.
I'm trying to figure out what's going on and calculate things, and I've been using the PARC one, and I was talking to Wayne about it. He's done some tests, and I can't duplicate them with my signal generator, which is a FieldTech one. I'm not sure why, but anyway, worry about that later. Ken, quickly, were you involved in the design of the PARC signal generator?
No, Dave. Dave was the primary one.
Okay.
I think Peter, myself, and Frank were doing some.
Oh,
I did all the kidding on it.
We did a prototype. I think a couple of us did some prototypes too. I think Frank did one as well, and to put it through its paces to confirm whatever Dave had designed. But I took a look at my prototype earlier, Michael, and I'm not sure I want to try and resurrect it.
Don't waste your time. I still think that you have to use the peak of the square wave because that's the I've looked in a couple of places, and that's the RMS value of the square wave is the peak, not the peak that 0.7, I think. You can talk about that later anyway.
Yeah. But one thing I don't really remember it being too off of whatever, I don't remember when I'm putting it through its paces, I don't remember whatever I measured on the output being that far off of what was quoted in the documents.
How did you measure the question is how you measured that output, I guess. I don't know.
Well, I probably. Well,
The only way I know to do it, I don't have a watt meter, so the only way I know to do it is take the voltage and calculate it from there.
Well, I either used my SA if I had it at that time, or I used the PARC SNA.
Oh yeah, I guess I'll have a look at that. I'll go take a look at that after. Yeah. Okay.
Peter, can you hear me?
Yes.
Okay, I just wasn't sure with looking at this mic whether it's on or off. I wanted to actually talk with Dave, VE3OOI, if I could have a minute before you get started.
If he's there. Well, he's there, but...
He was there. I just wanted to talk to him about that dynamometer I had made, because he was...
Oh, okay.
Oh, he's there. He's in a picture of him anyway.
Yeah. You could send him a text. Send him a text in the chat window.
I don't know how to do that, Peter. I might just get it. If he's interested, all I want is his email, and I'll scan them and scan the article and send it to him.
Yeah, my mouse has gone funny here. Uh-oh.
Check the battery. Can you not hear me?
Yeah.
Yeah.
Oh,
I can.
yeah, just testing the mic.
Okay, so 4812. Should we wait a couple more minutes and see who comes in?
Anybody hear me?
Yeah.
Yep.
Can you guys
My computer's going awful funny here. I may have to reboot.
hear me?
Yep. And see you.
No, not at all.
Okay, so who was asking to speak to me?
I was Dave, VA3 DLF. Don't even remember my call sign. You mentioned that you were doing some work or going to do some work on doing dyno testing on electric motors. Were you talking small electric motors like on model airplanes?
Yeah.
Because I wrote an article back in 2009 with a 6 or 7 page article here in a magazine called Fly RC, and how to make your own dynamometer. And
What's a dynamometer, whatever it is?
what is it? It was using eddy current brake.
Oh,
and
yeah.
You could actually measure torque and horsepower efficiencies, and it graphed everything. You may be doing something similar right now. I'm not sure. Yeah, okay. I've built those before. Yep.
It's just a test stand. It's got an Arduino. Hey, Eric, is Eric on the call? Eric, look at that. Look at that. You know what that is? Yeah, 3D printed custom case. Look at that.
Yeah.
Anyway, so yeah, it's got a load cell at the bottom there.
Yeah.
Okay, and I'm measuring the thrust. All I want to do is measure the thrust so I could figure out my thrust to weight ratio when I build models. So I know it's not underpowered.
There's a picture there of the dynamometer, and it actually measures your torque, your horsepower, RPM, everything, and it's all calculated and there's graphs. And it was actually within a couple % of the manufacturer's curves on the motors. I don't know if you'd be interested in that or not, but
Sure, send it to me.
what's your email address?
drajnauth@gmail. I'll put it in the chat.
Okay, all right. Good, that's good, thanks.
Okay, is Peter back yet? No. Let's see. Just wait for Peter to come back.
Yeah, because as I said, all I'm interested in, because the last airplane I built, I flew, I put the motor was undersized and it kind of just floated. So
Yeah.
I need to better get, you know, measure what the thrust is given a prop propeller, prop motor and battery, right?
Yeah.
So I just needed a thrust stand just to measure what the thrust would be. And that way I'll know if my airplane is properly powered, right?
Right. Well, your thrust stand there, I don't think would handle the motors that I've been working on, but
yeah, no, these are small models. You know, if you look up the ceiling, you'll see one of my models there.
okay, I see.
And you'll see at the back, you could see my helis at the back there.
Okay.
And here's my latest edition.
Oh yeah, yeah.
Completely scratch built drone, 100% scratch built.
They're a lot of fun, aren't they?
Yeah. So that's how I occupy my time.
I just finished, believe it or not, I just finished building a Heathkit HW104 last week.
Oh, really? Cool.
Yeah, I found it on Kijiji about it first week of February, and it took me the whole month to build it, and it works like a charm.
Is that strictly a 6-meter rig?
Oh no, it's the full. It does 80, 40, 20, 50, 15, and down into the 10-meter bands.
Oh, okay. That's cool. That's cool. Yeah, I did something similar, and hopefully at the end of the meeting, if I got 10 minutes, I'm gonna go through my my ham radio bio, and it's going to include my very first receiver back in the 70s.
My first was a Heathkit AR3 short band receiver. I never got into building ham radios until 5 years ago because I didn't have my license. But I bought HW100 and now the HW104.
Cool, cool.
Resurrected 6 Heathkits in the last 2 years.
Yeah, there's a lot of that going on right now.
That's kind of fun.
Yeah. I've been going through some of the groups involving the old Heathkits, and due to the pandemic, a lot of people are digging up some old Heathkits and resurrecting them.
Yeah. Well, I was very lucky to find these kits unassembled. That was really fun.
Yeah, that's a hard find.
It was.
Okay, what happened to Peter?
Peter seems to have disappeared.
Well, he had to reboot.
Okay. Oh, okay. Okay, well, let's give him a couple more minutes, and then we'll get started here, because we got a full agenda tonight.
How are you doing, Drew? V3UIN, how are you doing?
Yeah, I'm doing well. Dave, yourself?
I'm good. How's the COVID?
Well, it's over. You know, it's pretty well gone. I'm still tired.
Are you?
Oh yeah, it was a good 3 weeks.
Wow, that's not good.
Nah, you know, I can certainly see where it would be difficult without the vaccinations.
Yeah.
Oh yeah, no, there's no question. It was a good solid respiratory infection. There's no doubt about it.
Yeah.
Ooh. Were you hospitalized?
Oh God, no.
No. Okay.
No. It never got that far. You know, it was a really good, solid, you know, 1 week of nasty cold, and then the rest of it was just coming and going. But the onset was very fast. It was like 2 days and hammer between the eyes.
Peter's got an awful slow computer, doesn't he?
I don't know
Well,
what's going on.
The hand crank gets in the way.
Maybe he's charging his 12-volt battery.
I could be.
Anyways, let's get started here. Welcome everybody to the mid-month HB meeting. So we've got some presentations tonight. Dave is going to do part 2 of his journey down the rabbit hole. Wayne's going to talk P-Spice simulations in KiCad. And hopefully, if we've got 10 minutes near the end, I'm going to do my ham radio bio with a little surprise on the end. So if we're ready to roll, Dave, you want to go ahead?
Okay, you want me to go first? Can you guys hear me okay?
Oh, yeah. Unless Wayne, do you want to go first? It's up to you.
I can go. Doesn't matter.
No worries, I'm good. No worries.
Okay, go ahead, Dave.
Yeah, for some reason, I think what Peter has is contagious. My PC's not behaving well tonight. So hopefully this works, because all of a sudden it just crashed. So I rebooted my PC and hopefully that fixes it. Let me just share my screen here and let's keep our fingers crossed. It's going to work. Okay, can you guys see my screen?
Yes.
Okay, is it clear?
Yes.
Okay, good. So this is a continuation to my series of talks going down rabbit holes, why my head hurts so much. And just a caveat before I start, this is not a tutorial. It's not meant to be a tutorial. I'll quote our good friend Charlie Morris, that it's not a tutorial, it's a log of what I sort of learned, right or wrong, and it's just ramblings of an old experimental physics geek that hasn't done this stuff for years and years and years. So how it all started, just I'm not going to go through this whole thing again. I'll just give a 1 minute overview. So how this all started was I got an Ender 3 printer and I discovered that there's a laser module you could get for the printer that snaps on the printer. Can you guys see my pointer okay?
Yeah.
Yes.
Yeah. So, and this laser pointer allows you to go and etch paint off a board or burn paint off a PCB board, and then you can etch the board. Now, I was intrigued to see how this all works and how these laser modules work, because you can get, upwards of 10 watts of beam power. They advertise them at like, 20 watts or 40 watts or even 60 watts, but that's power consumption. That's not output optical power. So I was kind of interested to see how they work, and I found they use buck converters to take, because a lot of the voltages that are supplied to the print head is of the order, I think, about 12 volts or so. And these things are typically driven with low voltages, right? So they use a buck converter strapped on inside this to convert the voltage, step it down, and they also consume a fair amount of power. So that's this is the map of my rabbit holes. So I started out with laser modules, looked at the buck converter, couldn't figure out how that sucker works. So I had to go back and revisit how an inductor works. And the previous talk, I talked about that, inductors, about Lenz's law and Faraday's law, and how that all fits into what we hear about inductors. And in this talk, I'm going to focus on MOSFETs, because that's where the real reason my buck converter simulation wouldn't work was because I didn't really understand MOSFETs, or not really didn't understand them. I did a dull moment. I pulled a Homer Simpson, and I did some really silly things. So the agenda today, I'm going to just talk about MOSFET parameters and how they relate to the buck converter. I'm going to talk about high side and low side switching, because this is really important when you look at the MOSFET parameters. And depending where your MOSFET is in the circuit, that's going to tell you how you switch that MOSFET on and off. I'll go into Mosfet construction a little bit and then talk about the capacitance that's in a MOSFET. And we're going to look at the, I built my own MOSFET model in LT Spice, and we'll test that out, and you'll see how capacitance plays a role in these MOSFETs. So I'll be jumping, one thing I should note, I'll be jumping around a little bit here because sometimes I'll be talking about switching. So using a MOSFET as a switch. And towards the end of this conversation, of this presentation, I'll be talking about a MOSFET as a power amp. So I'm going to jump around a little bit because as I went through this journey, I wasn't really going through it to learn about MOSFET switching. I wanted to learn about MOSFETs and the power amp. And in a subsequent talk, I'll talk about the power amp issues I've been seeing. So what I originally did, just to try and understand how a buck converter works, was I ran across this design by this gentleman from some university in the States. And basically he designed a buck converter. It's got a MOSFET that's used as a switch, and he's got some design criteria. And basically the output he's trying to get is 12 volts out, 36 volts in, 12 volts out, and 10 amps into a 1.2 ohm load. So I went through, designed a buck converter, put it in LT Spice, and I can't remember, what's the guy's name? Friday? Was it Jack something Friday from Dragnet? So in our last episode, you know, I had shown this, and the output I was getting was millivolts and milliwatts coming out of here. And it turned out that I was not applying the correct VGS to this. And that was one of my dull moments. And so what I missed was that VGS, this is the parameter, the data sheet for the IRF 510, by the way. So the for the IRF 510, the gate source threshold voltage, which is VGS, and that's the voltage that you apply to the gate with respect to the source that turns that MOSFET on. So it's 2 to 4 volts you apply to the gate above the source voltage. So for example, if the source is grounded, the gate voltage is 2 to 4 volts and the device turns on. However, if, for example, the source is at 5 volts, the gate needs to be 2 to 4 volts above that 5 volts. So it needs to be 7 to 9 volts, according to the datasheet. The other important parameter for the buck converter was this RDS. That's the on-state resistance for the MOSFET. And this really bit me in the ass. And so for VGS of 10 volt and ID of about 3.5 amps, you get about a half a ohm across the MOSFET. Now that's important because that is going to dissipate the power. So you can have I squared R losses. So you've got 3 amps, you know, squared 9 amps, 9 squared, that's 9 times 0.5, which is about 4.5. So you're going to be dissipating 4 to 5 watts with this RDS in this configuration. So this is what causes the device to dissipate the power and get hot. So in this case, as I said here, for VGS 10 volts, 3.4 amps, RDS, they said it's 5.4 ohms. So I went back to LT Spice, and I thought, okay, let me kind of put in practice what I learned. And there's two configurations that when you're using a MOSFET as a switch, one is called a low side switch, where the MOSFET is on the low side of the load. So in this case, VGS, the source here is grounded. So VG applied is relative to ground. So here you would apply 2 to 4 volts. The IRF 510 would turn on, and that load current would start flowing through that load. Now, in the case of a high side, the MOSFET is on the high side of the load. And in this case, as current is flowing through this, load, you're going to get a voltage drop across here. So at the bottom of the load, the voltage is 0, but at the top of the load, the voltage is not 0. So your voltage, your gate voltage here, the switch voltage to turn this on, has to be higher of that voltage by that VGS. Okay, so I thought, okay, let me check this out, because basically if you look at the configuration I've got, it's basically a high side switch, right? Here's the MOSFET, and this is just the load. So it's a high side switch I've got, right? So I thought, okay, for 36 volts, let me put 4 volts on top of that, pump that into VG, and I'll plot VS versus VG, and lo and behold, magic happens. So the red trace here is showing the VG, which is 40 volts, and VS is 36 volts, which is what's being applied here. So 36 volts is coming across, and we have a happy cat. The cat's happy, no one's angry, everything's working. Are you guys still with me here? Can you guys still hear me okay?
Yeah.
Okay.
Yep, doing well.
Okay. So I thought I'd go back to the buck converter, and I put 40 volts in, 36 volts here, and I run my simulation, and I get 10 volts coming out, not 12 volts, and I get 8-ish amps, not 10 amps. So the cat's angry again. Something's wrong here. And so it's another dome moment here. After thinking about this, I realized that this is a voltage divider. So in a voltage divider, you got R1, R2, and that's the equation for what the output voltage is going to be, V2, given an input voltage in R1 and R2. So R1 is the MOSFET, which has an on resistance of 0.54 ohms, and R2 is the load. Now, in my simulation I just ran, I had a load of 1K. So half an ohm compared to 1K, there's almost no voltage drop. So that's why it worked out well. However, if you look in the buck converter, if you clump this load together, and if we just forget about the complex part of the load, let's just look at the real load, it's 1.2 ohms. So if we got half an ohm feeding 1.2 ohms, that would explain the voltage drop, and I'm not getting 36 volts here, which is powering the buck converter, because the whole point of this switch is to put the 36 volts here. So I thought, okay, let me go back and let me do another experiment here. So what I did was I said, okay, and I don't know why I used 50 volts here. I just had a brain fart. But okay, so I did the buck converter. I put, not the buck converter, I put 1.2 ohms as a load. I fed in 50 volts here, okay, and I looked at what the VS is. And so VS is here is in green, which is overwritten by the blue, and it's about 28 volts. It's roughly about 28 volts I'm getting here. So I'm not getting 36, I'm getting 28 volts. So I thought, okay, let me use an ideal switch, okay, turn that switch on and off at the same frequency that I'm pulsing this on, and I'll overlay that, and let me get smart. I'll put a resistance here, and let me calculate what the resistance here needs to be in order for me to get 28 volts. So I did a little bit of math, and it turns out to be 0.295 ohms. And so once I put 295 ohms in here, lo and behold, the curves match exactly, and the cat's happy again. So part of the reason why I wasn't seeing that voltage coming out is because I had a voltage drop across that load, and I needed to bump up the voltage that I'm applying to the gate. So the question arises now, you know, this is common for any buck converter that uses a MOSFET. If you've got a 12-volt power supply, okay, how the hell do you get greater than 12 volts to go and power this MOSFET? So I did some research, and I came across this thing called a high-side bootstrap. Okay, and they're actually chips. You can get MOSFET drivers that allow you to go and drive a MOSFET using a microcontroller, and it's going to generate a higher voltage at the gate to allow the MOSFET to operate in a high-side switch. So the way this circuit works, and this circuit came from this guy's YouTube channel here. So basically, just ignore this whole, this is just a buck converter circuit. We could just replace that with a load. So ignore that. So the way this works is that you've got a capacitor connected here, and it's connected to a diode that's forward biased if the voltage here is greater than the voltage here. Okay? So what happens when this MOSFET is turned off? The voltage here is 0, right? The voltage here drops to 0. So it's forward biased. And so this flows, current flows this way and charges this capacitor up. So this capacitor now becomes 36 volts relative to this point, which is ground. Okay, so we've got a little circuit, another resistor that comes back, feeds the gate, and a transistor here that shorts this to ground once I put a pulse on here. So once I put 5 volts on here, this shorts, this is ground, this is ground. VG is below VG, below the VGS threshold, the MOSFET goes off. So it charges. Once I turn this off, and this is allowed to now rise up to V-boot, then the MOSFET starts turning on. The voltage here now, okay, is added to the voltage here. Don't forget, this capacitor is charged up to 36 volts. So if this voltage here is at 10 volts plus 36 volts, we're at 46 volts here. So that's the way the bootstrap works. So, and if I plot the voltage here in LT Spice, you could see initially the capacitor charging up to 36 volts when it's off. When I turn this off, so this allows to turn on, right? You could see here it rises, and this is showing a almost vertical line, but it's not. There's got a bit of a slope, because as the voltage here increases, the voltage here increases, and it's a cascading effect. The voltage here increases as this voltage increases, so you get more voltage coming across. And the net effect, and you could see here, you could see these tops are going up. They're getting larger and larger as more switching cycles happens. So the top here, it's at 67 volts at V-boot when it's on. Okay, so I said, okay, that's great. Let me look at my V out and my current, and look at that. I'm getting almost 19 volts coming out. Okay, and I'm getting about 16 amps coming out here. This thing's generating about 16 amps into that load, and it's about 19 volts here. So this is working fantastic. However, here's the problem, is that if you plot VG minus VGS, so VGS, I plotted VG minus VGS, VG minus VS, right? And if you look, it goes up to 35 volts. Okay, now if you go back to the data sheet for the IRF 510, it's only rated to plus minus 20 volts. So I'm going to smoke this puppy if I was to build this. And this is one advantage of using LT Spice. Why I love LT Spice so much is that you could run scenarios like this and you could figure this out. Now you can, these MOSFETs, you can pulse them, but I have a feeling that I'm gonna burn this sucker out. So you need some way now of taming this or replacing this with a better MOSFET to make it work. So in order for me to get my 12 volts coming out and my 10 amps, what I did, I put a voltage divider here and I played around with values and to this R4, what value of R4 I need to get a 12 volt output here. And it turns out that if I put a 1.25K resistor here, I get 12 volts and 10 amps coming out. However, if I measure the power being dissipated in this IRF 510, it's 100 watts. And the maximum power dissipated from the IRF 510 is 43 watts. So I'm definitely going to smoke this sucker if I was to build this. Now here's an LT Spice trick. If you want to see the power plot, hold the Alt key down and click on the component. So you'd hold the Alt key down, click on that component, and a plot comes up showing you the power. And then if you hold the control key and you click on the trace, it'll integrate or give you the RMS value of the power over that period of time. Okay, so I'm going to switch now. I'm going to talk about Buck, but I'm also going to talk about power amps. So we're going to talk a little bit about Mosfet construction here. So I've got a little video, a little animation that shows how a Mosfet is constructed. It's only like a minute or so long. So a Mosfet starts out with a P-type substrate, right? Something that's P-doped. And then you have two N-doped regions. And those N-doped regions becomes a source and a drain. Then you add a layer of oxide, an insulator, and then you add a metal layer, an actual metal layer, and that becomes the gate. So all of a sudden, this forms a capacitor. You've got a metal gate, an insulator, and the P substrate here. So basically, this is one giant capacitor. And that's why a MOSFET draws very little current. It's like an op-amp. Very little current flows across because there's no direct connection between the gate and this P substrate here. So as you go this now, there's an insulated region here, and nothing can flow between the source, drain to source. Nothing can flow because it's insulated. So now, if you start applying a voltage at the gate, what happens? You apply a positive voltage, it's going to attract the negative electrons to the gate. Okay, and it's going to push away these holes. And across here, it's going to attract electrons across there. And you can see that, and they call that the channel. You can see it drifting apart, right? And all of a sudden now, you're starting to form a channel. And as this voltage gets higher and higher, this channel starts to open up. And you can see the channel open up. And the minute that this channel is complete over here, current starts to flow. That's your VGS. That's your threshold voltage. Okay, so the voltage with respect to the source. Okay, and that opens up the channel. And by varying this voltage here, you're basically pinching off this channel. and allowing more or less electrons to flow. And there you could see the electrons starting to flow. Pretty straightforward. Now that's all I'm going to go into in terms of the Mosfet construction. I just want to show you that just how you've got these layers and you've got a capacitor here. So if you go back to this model now, if you look at this, you've got a depletion region here, you've got an overlap, you've got another area here. These are all capacitors. These are all going to form capacitors. And here's a model showing all the various capacitors you've got. So this MOSFET is just riddled with capacitors all over the place. Okay, and here's a model to give of a MOSFET. This is the gate drain capacitance, and I think that's sometimes referred to as the Miller capacitance. Then you've got the gate source capacitance, and you've got the drain source capacitance in here. So I thought, okay, let me get smart here, and let me make a model. So I go in LT Spice, and I said, okay, in my IRF 510, I know what the input, output, and reverse transfer capacitance is. Okay, here it is given in picofarads. Let me create this model. There's my RDS, which is 0.54 ohms. And let me create a model, and let me see how well this matches up to an IRF 510. So there is a gate resistance, which is small. It's 11 ohms. Now keep in mind, because you've got all these capacitances and you've got this gate resistance here, this is going to form an RC circuit. And these capacitors have to charge. So that's something that in a power amp, you have to take into consideration how fast, what frequency you're going to be applying to this. So I went on and I compared the IRF 510. I use an AC source, and I fed an AC voltage of 1 volt coming in against this model I created here. And in the model, I found some calculations how to calculate the various capacitors here. There's some formulas how to calculate them. I ran across those on the internet, and so I plotted it. So here is the voltage divided by current, which is the impedance, same voltage divided by current. For the green is the actual MOSFET, and the blue is the model I created. Now, if you take a look at this, look how close they are. And if you look at the difference here, which is pretty, this is the biggest difference between them, it's about 1 ohm difference. So the model that I developed is actually pretty accurate in terms of predicting the performance, the input performance of that MOSFET. Because as I go forward and I look at what's happening in a power amp, basically it's grounding. It's getting grounded at these higher frequencies. The MOSFET is just shunting the frequency to ground because of all those internal capacitances. So where am I here? Okay, I'm over here. Okay, so another thing to think about, I talked about charging those capacitance. So if we go back to the buck, we do the input capacitance of the MOSFET, it's 180 picofarads. I just did a simulation here with just 1K because I wanted to get a slow rise. If I didn't put a resistance here, this thing would rise very, very quickly. I wanted to slow down the rise, so applied 40 volts. So this is like applying 40 volts to the gate and applying 10 volts to the gate. And I said, okay, let's say the threshold voltage is 5 volts for this to turn on. Well, the 5 volts, to reach 5 volts, the 40 volt, the 40 trace here arrives at it sooner than the 10 volt trace. So that capacitor charges up faster to the 5 volts, and it charges up 102 nanoseconds faster. So this is really important because it means that we may have to apply a higher voltage to get that MOSFET to turn on. And with power amps, that's why our performance of the MOSFET, the power amp, deteriorates with frequency, because we have to put a lot higher voltage in to get that sucker to turn on because of the capacitance. So I only have a couple more slides. So what does this mean? Okay, so here is, I plotted a IRF 510 versus a RD16HHF1, applying 5 volts across. This is like a low side, right? I'm just looking at how the input impedance changes here. So if you take a look at this, and I plot both of them, and I plot both the real and imaginary, you'll see the impedance coming into here is purely complex. It's purely, imaginary. And that's purely coming from the capacitance. And you'll see the IRF 510 has a lower imaginary capacitance, impedance than this RD16HHF. Okay, and here's an LT spice trick. If you want to look at your Cartesian components, you want to get the real imaginary. When you go into select, you right click on this side of the plot, it comes up, and you go in here and you select, instead of bode, you go down, you say Cartesian, and then it's going to plot, it's going to give you the real and imaginary. The imaginary is on this side and the real is on this side. So what I did was I went to DigiKey, and I thought, okay, well, maybe I just need a better MOSFET. This IRF 510 is a piece of crap. So I went into DigiKey, and I did a whole bunch of searching. I did parameter searches to try and get devices with the smallest capacitance, input capacitance. The smaller capacitance, the less effect it's going to have, right? So I went and I started searching, and I found these devices here. And so for each one, I did this, and I did this the hard way. Sorry to say, for each one of these MOSFETs, I generated a plot, and I manually measured it at 1.9 megahertz and 14.1 megahertz, and I plotted it. Now, in a subsequent talk, I'm going to show you how you could do this a lot easier. So if you look at this, you know, at 1.9 megahertz, you could clearly see the blue guy, this RD16HHF, is clearly the winner, because the input impedance is kiloohms, right? Whereas if you go out to like 14.1 megahertz, you can see they're all starting to short out. And if we magnify this and we look around the 10 meter band, okay, and we say, okay, let's plot the impedance, the input impedance of these MOSFETs around 28 megahertz, and let's look at that. And you could clearly see that, you know, 50 ohms is down around here, 50 ohms around here. So you could clearly see the this RD16HHF MOSFET has got, you know, 100 and something ohms of impedance, right? And this this red guy, which is the VSH8, you know, they're clearly winners here that are potentially good MOSFETs for higher frequencies. So that caused me now to think, because I ran across this, I started to think about my D612 power amp and the problems I was having with that. And I went and revisited that. And in my next talk, I'll talk about power amps and the problems I had with the 610 and how I went about selecting an appropriate MOSFET. And that'll lead me into talking about the spectra purity of the output from a MOSFET, and as well how to make automated measurements. Because for me to go and run FFTs on every single one of these and manually calculate it, it would take me days and days and days. So I was able to go and do this within minutes, getting the data by using measurements. So at that point, I will say Finn, and I'll turn it back to you, Ken. And if there's any questions.
Any questions or comments? Go ahead, Hassan. If you're talking, you're muted. Hassan?
H-Man, you're still muted.
He says he can't. He says he can't come back to you. He wants you.
Oh, can you hear me now?
There we go. Yeah.
Okay. Sorry, there was a pop-up that said allow microphone. Okay. Yeah, I had a question, Dave. Negative real impedance.
Yes.
What does that mean?
I forgot to mention that. That threw me for a spiral. I went looking at that for negative, because in one of the, if you look at the complex, you look at the complex impedance, the real impedance was negative. And I went looking to understand what that means. And Hassan, you might be able to explain this better, but they were saying it has to do with a phase shift. And they said it has to do with the direction the current's flowing. And the way I measured the impedance, the way I measured it backwards because the current is out of phase or it's flowing in a different direction, or I may have a different source. And sure enough, in my drain, I've got a voltage source there, right?
But it shouldn't. Oh, so current is going from the drain through the gate out the other way?
Yeah, I don't, Hassan, as I said, I didn't understand it. I Googled it and I read a couple of articles, and the one I found, which seems to be most authoritative, the guy said that's normal. He said it's also common with MOSFETs. MOSFETs, you will see a negative real impedance. And he said that it has to do with a phase shift, some sort of phase shift.
Yeah, I'm just trying to figure out where you get that phase shift from with an RC model, because it's a single pole model. So
that's why I said, man, it's above my pay grade. I don't understand it myself, but
mystery.
But I saw several people talking about MOSFETs saying, yeah, it's normal to get a negative real impedance when you're talking about MOSFETs. I don't know.
You have to go on YouTube and claim you found negative energy or something.
Yeah. I don't know, Wayne, if you've got any insight in terms of what that means. Yeah, so if anyone knows, go down that rabbit hole. I'm not going down another rabbit hole. Enough for me.
Come on, Dave.
Dave, one thing that you've used a lot of tricks associated with plotting things and calculating things from plots and stuff with LT Spice. It'd be really nice to have that sort of summarized somehow so we can try it ourselves. I mean, could you sometime put it down on a piece of paper or something, or do a presentation on those kinds of things?
Michael, to be perfectly honest, whenever I need to go do something, I can't remember how to do it, and I have to Google it. I'm not kidding. I go and I Google and I'll say LT Spice RMS value, how to calculate RMS value, or how to calculate power.
Okay.
Anybody else with a question or comment? Go ahead, Dave.
It was Peter.
Can you hear me?
Yep.
I really like what you did with the doing your own model there, Dave. That, because I thought, LT Spice would be a good way to learn some of these finer details. And I thought that was really smart what you did there. And then comparing it to the 510, boy, that gives you a lot of confidence and you're on the right track. When you looked at the new MOSFETs on DigiKey, what was the price of those MOSFETs like? I guess you've already selected one, I think, for the D612 to try. What is it?
Oh, spoiler alert!
Here it comes.
Half of them will blow up because they don't support the power output. It's a trade-off because to do a power amp, you need a power MOSFET because you're going to be dissipating a lot of power through it. And so typically, if you've got a small capacitance, you've got a small power loading or whatever it's called, power dissipation. So what I found, a lot of the MOSFETs, which look great on paper, the specs, if you look at it, if we put it in a power amp, we would smoke it.
I know this probably don't want to consider this one too much, but have you thought about what about paralleling them up?
Yep, look at that.
I know that's other challenges, but
I also did a simulation with it in parallel, and I think, again, remember we had a conversation a month or two ago about Tony Parks, about that push-pull, because I started to look at the push-pull configuration Hans Summers did for his amp, and you pointed out that Tony Parks did the same thing. So I went down that path, Peter. Instead of paralleling MOSFETs, I looked at doing a push-pull, because right now we're only pushing basically half of the cycle we're pushing through. With a push-pull, you're pushing half cycle, and then the negative half cycle, you're pushing that. So you're pushing both cycles and then recombining it. So you're getting twice the power going through. So I thought the push-pull configuration was a lot more efficient, and that's why I landed on that. And you'll see when I do my MOSFET calculations, you'll see I land on that, and I'll do the calculations and the FFTs using that configuration. Spoiler alert.
thank you.
Okay, anybody else?
And if no one has any.
Oh, Dave just
Hi, Dave.
up.
Frozen. Hello.
You're
Can you guys hear me?
Yeah, you froze there for
Good
about
now.
15 seconds.
Yeah. Okay. I froze. So are these presentations of value, or do you guys get it? Is this deep enough? Not too shallow? Like,
Well, I think it's great. I think
I like
it's
going
great.
there. Keep it up.
because it'd be good to get feedback, so I know, because I do put a lot of time into doing this. I don't mind doing it. I love doing it because this is how I learn doing things. So I don't mind doing it, but I want to know that you guys enjoy it and you guys get something out of it.
Oh yeah, sure. Yeah, it's really
Yeah.
good.
Absolutely.
Dave,
Yes, sir.
may I be excused? My brain's full.
Your brain hurts?
My brain's full.
If you were at
Well,
lots of
Super Nintendo Chalmers.
your brain should be empty after that nice long vacation.
Dave, can you post the presentation so we can look at it later?
Yeah, as I said before, yeah, I don't mind, no problem. The problem is it's one big gigantic PowerPoint spreadsheet, and I don't want to post it because I'm still working on it. So I could split it up if you guys
Yeah.
want.
Dave, do it. Save it as a PDF, and then just
Yeah.
post the PDF. It takes way less space.
Yeah, I know, but I just don't want to post the whole thing because I haven't finished it. It's just one gigantic. Right now, how many slides am I?
I know what you're saying now. Okay, yeah.
Yeah,
Oh, wait until you're completely done then, maybe.
I'm up to 70 slides so far, and I'm not done because I work.
Dr. Freeze.
What's that thumb going across my screen?
Elvis has left the building.
I don't know what's going on with my PC, man.
Now you got two instances of your camera. The other one's blank.
Okay, how do I stop that then?
Who knows? It doesn't matter. It's okay.
Try, it says kick out. Let me try kicking myself out. There, I did. If you right click on the participant, you can say kick out. So I kicked myself out. Seems to work.
Okay.
Okay, I'll stop talking.
Okay, we got a couple hands up. Michael, go ahead.
Yeah, while Dave's presentation was going on, I think I got kicked out a few times. The screen just went blank, and I had to go back and start over. Did anybody else find that happening this time?
Maybe
No.
it should.
I was having a lot of problems too, and I had to reboot my computer. I've also had to come in and out a couple of times. I used my phone.
I think someone else had their hand up.
Recording is on. Recording
I
is
didn't
on.
catch who it was. Anybody else comment?
I just like to say I think these sessions are very useful
Yes, definitely.
for learning.
Let's move. I want to say thanks, Dave, for all the hard work you put into your presentations. Who's up next? Oh, Wayne. Wayne with PSpice Simulation and KiCad.
Okay, so let me do the ritual sharing of screens. This is going to look weird for a second. You might want to close your eyes. Okay, I should be sharing my screen, and you're probably looking at LTSpice and KiCad. Is that correct?
Yeah.
Yeah. Yes, sir.
Okay, so let's start the presentation. I just want to. I'm using a presentation mainly as crib notes, but I'm going to talk to how I'm going to do this. I'm just going to do a very short comparison of KiCad's and NGSpice compared to LTSpice, so you get a kind of sense of how they fit together. I'll do a very quick demo to show you the simulation itself of an active filter. And then I'm going to do a transistor amplifier section where I'm going to talk about how you actually feed the simulator to get it actually working in the first place. Okay. Now I've been having a lot of troubles getting this stuff to work for me. I happen to be a good stupid user. Nobody does stupid user better than me. So pretty much anything you can do wrong, I've been doing it until I learn how not to. So I will share some of the things I'm seeing. Try to leave out the stuff that was just white noise, I guess, in the experience. All right, so let me just go to the next page here. Okay, here we go. Sorry for the noise. Okay, so what I wanted to say while you guys are staring at the screen here is, so LTSpice is a purpose-built simulator. So it has a schematic editor bolted on to an implementation of the Spice tool. So the only reason for the schematic editor is to make it easy for you to model a PSpice netlist without having to actually write it by hand. Okay, and it's been around for over 20 years, much 2 decades longer than KiCad's version of this with NGSpice, and so it's pretty robust. Okay, the editor is integrated to the simulator quite well. The analyses, I would say, when you compare to what's coming out of NGSpice, they both basically have the same raw capability. KiCad offers them as KiCad is responsible for the front end NGSpice, and it has places where you can do data entry to set up Spice simulations. I would say LTSpice seems to have more data entry screens for it, but if you can learn how to do .op commands and put them onto the text of the picture, you can do anything in KiCad that you could do in LTSpice in terms of simulations. Now, KiCad is essentially, it's a PCB file generator, and it has it has a schematic editor to allow you to design the schema that is going to be turned into PCB. Quite recently, they joined forces with ngSpice to allow you to also do simulations. So when we look at what we're seeing on the screen in a moment, what's going on is KiCad is basically providing ngSpice with a representation of what the circuit is, because you've got a circuit editor. It passes that to ngSpice. ngSpice does the simulation and returns data back to KiCad, and it's displayed. It's my understanding it's KiCad doing the display, and it's certainly KiCad doing everything surrounding it in terms of what you have to data enter in order to get the simulation to work. And ngSpice is pretty much an invisible engine. There's only one thing that I can attribute as directly coming back from ngSpice. And let's go have a look at that. So I'm going to bring up the KiCad. Here is a representation. I have this in LTSpice as well, because what I was doing is sort of saying, okay, what does LTSpice tell me? Does KiCad agree for the longest while? So I'd share that. So this is a silent key filter, low-pass filter. The way you get at a simulation depends on which version of KiCad you're using, okay? I'm using the latest version, and since I think it was the last version before version 6, they added a capability into the tool that allows you to just go into the simulator and start with the sim parameters. You always could do this, but what's different is this compatibility mode is a menu item inside KiCad today. If you're using an earlier version, the compatibility mode is actually unavailable on screen. You have to have a file on your drive called .spiceinit, and it has to have a certain little text string in it to inform the ngSpice simulator which version of Spice it's supposed to be simulating under. I have it set up to PSpice and LTSpice. You can go Spice, whatever that is, LTSpice, PSpice, and HSpice. These are versions that I, honest to God, can't tell the difference between them. I've tried reading up on them, but I really couldn't say. The types of simulations here are AC, DC, operating point, transient, and custom is basically going to let you type in anything you want. What you're seeing here is actually on the schematic screen. So it's akin to how LTSpice does it. With LTSpice in a simulation, when you go to simulate, edit the simulation command, it's quite similar. It's got noise on it as well, and I think there's a difference between sweep and transfer. These analyses, I believe you can do as a custom analyses in KiCad if you choose to. Another thing is you'll see type of sweep showing under the AC version in LTSpice, but not in this one. So what's the difference is, if you really want to get exactly the same capabilities, sooner or later you may be just typing the .ac command in here. With LTSpice, what you do is you type in something here if you're lazy, like I am. It actually tells you what that looks like, and when you hit OK, it's adding it onto the actual schematic anyway. So this is what LTSpice is running from. It's what's running from what's on the screen itself. Okay, with KiCad, maybe a little different. So anyways, I'm going to just do a custom simulation and start now looking at what you see on the screen is an empty screen, much as this would be in LTSpice. You've got to tell it what you want to see. There's an add signals thing at the top here. Oh, I've got to run it twice. I should show you the bottom here. This little white spot here is actually a rolling text box. That's where information is being sent to us. It's like the communication window between ngSpice and KiCad. So I got to run stop once, and it's run the analysis. It's giving me some feedback. From experience, I can tell you this is not a fail, it succeeded. You get some seriously strange looking error messages if ngSpice disagrees that it got what it needed. These are some warnings. VG1 has no value. I may have time to tell you what that really is. Data rows, don't really know. It's telling you that it's got a default temperature setting, which is interesting because it's higher than nominal temperature, room temperature. I guess it's allowing for, it's running a simulation on the potential for a part to be slightly warmer than room temperature after heating up. If you select add signals, you get to select the signals that I've identified on the schematic, which you no longer can see because it's covered. I'll just add this because I want to show, first of all, just a comparison between the way the two screens are rendered. Oh, I'm done, so I should say OK. So the LTSpice version versus the KiCad version, and I think it's KiCad doing the rendering. They're similar enough. They work the same, identical. That's the same picture, I guess you'll agree, for the amplitude. It looks like it's a different chart for the phase, but actually it's how they chose to draw it on the screen. So if you look at the way LTSpice does it, it generally tries to put the 0 degrees at the top and scroll down, so you get a contiguous 360-degree roll. This one starts 0 in the middle, and as a result, it runs out of wiggle room. So it zips up here and continues the curve and goes down there. So you will see that. It's not necessarily a bad thing. It's a little hard for me to understand, but I'm not plagued by it because normally I'm just looking at the amplitude anyways. So they're about the same. LTSpice, of course, has lots of features that you've heard of and you're probably familiar with. You can do all kinds of changes to the display. There's not so much you can do with changing the layout of the display. It's driven simply from the simulation command. You can zoom in, you can zoom out, and if you manage to lose your track, fit on screen restores the screen you're looking at now. So I found myself lost looking at a narrow edge of a line here once or twice. Fit on screen is what sort of fixes it for you if you ever get lost using it. You can also use a probe, which I won't trouble with, but you just sort of point at something. Let me try that. If I hit it dead on, I will have added the input. Now, there we go. So the probes work, and that's, I guess, similar to how it does it in LTSpice. You don't see sort of like if you click on a point in the graph here on LTSpice, you'll see where you are in the graph at the bottom of the screen. Here, which I've covered it up, it's a little bit harder, but not much. Basically, you can see, if I make this a full screen now that I can talk to it, you can see that there's cursors here. You enable a cursor by right-clicking the signal, show cursor, and it draws it for you. And here we are, frequency at 56 Hertz, gain is 0, phase is 0. It's not working, and I don't know why, because I'm giving you input, that's why. Dumb. Let me just hide that. I'm going to hide the signal because I don't need it. Be out phase, please. Show cursor. Be out in magnitude. I'm going to hide the signal. That makes it easier. Be out phase, so you can see how the phase walks like that. If I want be out magnitude, show the cursor. It starts in the center, and you can walk it around. And what it does is it shows you on the side the values that in LTSpice you generally see at the bottom. There's no focusing the cursor on a part and getting the power dissipation, that sort of stuff, as yet in the KiCad version, but it's still green. Dave mentioned he'd like to see tuning. So let us tune something. So it's in the way. There we go, tune. I can change the value of these two resistors here. Okay. It starts at 2K. If I want to roll this up, I can get to say to 4K, and I can get it to 4K, and you can see that the frequency got lower where the curve turn south, as it were. This is actually representative of a problem I'm going to talk more on. And it's like this. The two save buttons are, if you actually like the design you got and press save, what it's there for is to overwrite the values shown on the diagram. So if you like that, you hit save, save, and 4K will appear where 2K was on the diagram. But I'm going to say I don't really like that. And there's no cancel button here. But I have no problem with the way it was before, so I'll just close the window. Okay. Hopefully I'm still there. If I were to go into this, I'm now going to start showing you where the data resides. This resistor has a value on screen of 2K. So what you see on the screen is what you expect the simulator to be using, because you didn't save anything. But if you chase it down, how you find where the SPICE model is, it's on the bottom to the left of the OK button of the edit button on all different objects you might point at. And here it is. Oh, 2K. Well, that's nice. The last time I ran this, it was still at 4K. So it has a habit of doing that. So one of my complaints is there's inconsistent results depending on what you're doing. And I'm telling you, I did the same thing just before I ran this, and I got a different result. You are free to disagree with that, because it's, as far as I can tell, it's hypersensitive to the order that you would do steps. But it doesn't necessarily have the same value here as you do on screen. For example, I think if I type 4 here, it still says 2 here. Okay, so what I'm going to try to point out, this is a bad design construct, in my opinion, as an software designer. You have 2 locations where the value that is shown here are recorded inside the software. Sometimes you can get them out of sync. And if you're unaware of that, the simulation that you run will not be the simulation you get if you build a circuit. If you build a circuit, you won't get the same results because the simulation is seeing different data. More on that later. But what I did want to do is just sort of go over the simulation, the things you can do of it for the first step. I am not thinking there's very much else to show you. I will mention that if you're on version 5, simulator is under Tools. It's under Inspect now. As I was doing a custom, I'm just running it again. And I can add a signal, which I can't see because I've got my camera sitting in front of this thing. I'm going to run the simulation, then add the signals. These are just various points in the circuit, as I guess you would understand. They're identified on the schematic. Normally, you're looking at in and out, and that's all you do. Okay. Now, before I go into showing you how you actually key in a simulation, would there be any questions about the simulator itself? It's basic, it's simple, and it works, kind of. I'm not fond of the phase, but I can't say very much else about it. Again, the bottom window underneath that simulator is where you'll find errors if they occur. Okay, so by the way, I can't see hands going up in case there were any.
Yeah, I got a question.
Yeah, sure, Dave.
Yeah, it's.
You did have a question.
That was a good question. Thank you, Dave. Carrying on. I think I might be able to do this safely. What I got to do is just close my file. I'll discard changes. Go back to KiCad. I'm going to go to the one where I'm going to show you everything else.
Sorry, Wayne. I got kicked out again.
Shame on you. Chich, chich.
I got a question. Very good, by the way. This is very, very interesting. Did you see a way that you could measure deltas? Like one of the things I really like about LT Spice is, you know how you could do the cursors?
Yes, I know how you, there's no way to measure it. I didn't try typing in V1 minus V2 on the command line.
No, I meant like, can you set 2 cursors up and look the difference between, like if you've got some frequency, it shows some waveform, and you want to see the frequency. One of the things in LT Spice, you could set a cursor to the hump of one wave and the hump of the other one, and then it shows you, it tells you what the frequency is, right?
I don't think I saw that, and I don't think it's available.
So it's only one cursor you can set
No,
up.
it's as many cursors as you have signals on the screen, but you're talking about showing the difference between them.
Right, right.
What it's going to do is going to write the data down in this panel here, but I don't think you'll be doing it like an A minus B kind of thing like it shows. So,
yeah,
yeah, okay. Do you need to see that? Because I can.
No, that's fine. I just wanted to see if maybe you stumbled across that.
Yeah, no, it's showing the two values on the screen. If you click on the two values, it won't show you the difference between them like it does on LT Spice. So I'm going to just change, please, to a different view. This one is, I like this one a little bit better for this part of the talk. It's actually no reason other than I like it better to really change. I have a simple transistor amplifier. It's not really a good realistic implementation, but I can talk to some of the things you need to know here, I think, a little bit more easily. First, to do a simulation, you need to be able to add the things to do the simulation. Resistors are resistors, capacitors are capacitors, they're passive. Transistors, well, you can find them, of course. They're symbols. These little guys here, like the power sources, when you want to place them down, what you're going to do is you just want to filter on Spice. And in fact, there's a couple of different Spice sections, P-Spice and Simulation Spice. And if you're using an older version, you might actually see 3. I believe I've done that. To be honest, what you're really interested in is Simulation Spice for the voltage stuff, because pretty much everything else is native to KiCad if you get used to it. It also has op amps, so this has the natural. This has the same kind of simulator that you find in LT Spice, where it has. This would be op amp 2 if you're looking for it in LT Spice, where it has 2 input pins, 1 output pin, and the voltage pins. So when you're doing simulations and you're not trying to use a real chip in order to turn it into a KiCad PCB board, this is actually quite convenient. And the reason is the pins are in the right order for the model. So I guess I could talk to that first. I'm looking at an op-amp. How subcircuits and models, that's like transistors and diodes are models, op-amps are called subcircuits in Spice terminology. They have parameters that are fed to them. With models, the parameters are predefined. They don't even mention them. You don't name them. The Spice interpreter knows how to invoke them, and it does them in a very particular order. With subcircuits, which is represented by an op-amp, there is a particular order by default used by all op-amp schemas, and that is when you actually invoke the model to cause a simulation to work, you pass it parameters which are the plus voltage, the minus voltage, the output voltage, I'm sorry, the plus input, the minus input, the output, and the plus or minus source power supply. If you understand that, what you're understanding is KiCad will use pin 1, pin 2, pin 3, pin 4, and pin 5 on whatever it is you're using as a symbol to feed the simulator. Now, sometimes that doesn't work. So now, let me just do 2N3904. Okay, I'm going to add this to my diagram to show it to you. And I'll add it here. And I gotta just bring this over to the center here. You know, toggling between Spice and KiCad is maddening. I want you to see the difference between the two transistors. The pinout on this one is 1, 2, 3. Pinout on this one is 3, 2, 1. I'm using this pinout to avoid having to do something, which I'll now show you. So what we're going to do is go into the transistor. I'm going to access the spice model section. And the things you have to do is give it a model. So if I select a file, if I'm lucky, I got to go to spice models, sorry. I won't find it until I go to spice model, spice files. I can provide it with a spice model. Okay, so I've got a single transistor in this file, and it's called Q2N3904, and that causes it to actually have the appropriate spice code for the simulation, except for one thing. There's a 3, 2, 1 here. So I have to inform you guys, sadly, that for this simulation, it's passing the emitter, then the base, and then the collector to the model parameters. And that ain't going to work because spice requires it to be collector, base, and emitter. So you really need number 1 to be collector, and number 2 to be base, and number 3 to be that. So you'll find this a situation happens quite a lot. I found a way to get around it sometimes. So the way you get around it in the normal way is you go down to the bottom here. See, it says alternate node sequence. You take the pins that are showing on the screen and you put them in the right order. I only have 3, so this is easy. You do that. It's actually in 3, 2, 1 order, and it reverses the pins to the simulator and fixes that problem. The reason that this is the way it is KiCad has existed long before it ever became a simulator. The simulation guys are using a different, I guess, mindset than KiCad had to begin with. So most of the out-of-the-box items are based on pinouts that may not actually work. And you have to be aware of that, and you have to be prepared to map them to whatever the model or the subcircuit requires. If I'm loading a subcircuit, you'll see it right on the screen, and it'll tell you it will tell you what it expects as parameters, which makes it easier for you to figure out which pins need to be where, and figures out how you do this alternate node sequence when you need to. Okay, I'm telling you this because I'm going to dodge it. Okay, I'm just not going to do it. An alternate for certain items allows you to get by it. So I'm going to show you the transistor dodge. I'm going to place, add symbol. What you do is just type NPN. And you notice that they've got a bunch of variations here. They're there, and I think they were added. They're there basically to allow you, from my perspective, to use a simulation. So this is CBE. This is the one I actually chose. It's got C first, B second, and E third. And that's what these letters are for. They tell you what order the pins are in so that you can work out which one you want to use. And I recommend you do that. So why do I recommend you do that? Well, there's another interesting feature of LT Spice. You saw me enter the sequence of pins, right? And I hit save. Where are they? They're not here anymore. Oh, what does that mean? Well, fortunately, there's an alternate pin assignments screen here. So let's look at that. Whoa, wait a minute. Here's where they go. They're not there either. So because it disappears, these pins, sometimes when you're struggling to get your, says Wayne, who is stupid user number 1 in the world, sometimes when you're struggling to get your model to work, it's hard to deduce whether you've mapped the pins wrong sometimes. So I'll just say once in a while, for you, maybe never. If it doesn't actually tell you what pins you've got to assign, if it does that. So this feature, I assume, is just, it's a user and user issue. It's a UI issue. It will go away eventually when somebody realizes that it's a problem. I'm not here to complain about that. I'm just want to warn you. Where you can get away with it, you should be able to find for the simpler parts that you don't need to. When you get to complicated op-amp, incidentally, you're actually going to have to do your own PSpice model. Let me place one more. That symbol, TL064, say. If I were to go to TL64, here's a problem with the TL64. You notice that it's actually 5 units. This is a case where this is the case whenever you have an IC that has duplicate copies of some kind of module on the board. An op amp is a classic one. It's got, this is a quad op amp. It's got 4 of them. And the 5th is actually a power supply. If you try to use this in a simulation, you can't because it requires 5 pins on this object. So when you come across that situation, there is a workaround. For brevity, I'll say look it up because it's really kind of hard to talk to. Basically, you do a very simple, spice model that includes copies of a generic spice model and feeds the voltage into it. You're going to find that in simulation with KiCad. You only find the good information about KiCad on the ngSpice sourceforge.net access. I've looked at KiCad and never found anything that I found quite useful. By the way, ngSpice has an awesome manual if you want to learn about spices. It's better, I think, than trying to find it out by, plowing through the LT-Spice help system. Although there's probably some differences that I'm not aware of that will cross you up if you're careless. So back to the model, back to the right model. So anyways, if you're dealing with the complex items, you might have to actually write your own shell around it, and you really want to look that up first. For transistors, I recommend you find one that actually follows the model. I will say, if you look at JFETs, you'll notice that they have various different pinouts. That's there for the same reason. What is it, MFET? What's a MOSFET? Yeah, there it is, NMOS. So again, same story. They've got different variations of pinouts. If you know what the pinout is supposed to be, you can just go there. How did I find this out incidentally? Do I still have it? Yeah, you go to any spice screen. What am I looking at? I'm looking at the Berkeley Spice. And if you look at a transistor, which I carefully scrolled off the screen, it gives you a hint here. See that? 1, 2, 3, collector, base emitter. That's how you know. So you want to get comfortable to looking it up. Okay, that's all I would say. Because you're going to need to for the models. That's diodes and transistors, and I don't know what else is in the model space. Back to KiCad. The resistor is the resistor and the capacitor and also the inductor. They're ideal capacitors, ideal resistors, ideal inductors. Whereas in LT-Spice, you can modify a bunch of parameters that allow you to deal with spurious side effects caused by high frequencies and things like that. If you need to have an accurate capacitor, you'll have to build your own subcircuit. Ditto for an inductor. Resistors generally, I think the resistor model doesn't really have any of those extra features in it. What else can I tell you? This guy here. Let's place a power supply. And again, that's Spice or P-Spice if you're in that. I'm going to go with that's VDC, that's VAM. What's my voltage that I normally use? Come on, where are you hiding here? Well, what these things here are here for, and it's useful to know, is they will actually hardwire into the actual thing you're trying to do. You may want to use them. I'm using this guy. I think it's in the other spice model rather than the one I chose to go from. So if I do spice again, yeah, there it is. Yeah, that's the one I happen to use, I think. eSource. Yeah, I think that's the one I used. I might be using an older model. Doesn't matter. It'll all work. There it is. That's the one I was using. And I think I'll stick to it for the reason that I want to show you some gotchas. When you enter this thing, there's a reference in a thing called vSource. Generally speaking, if you know what you're going to do next, you might do something like DC1, AC1, I'll make that DC0, AC1 like that, okay? Then you hit OK, and you connect it to your circuit. I want to go back in and show you what the spice part of the model is actually showing now. It correctly populates the DC and AC magnitude if you do that when you start up. Sometimes I've found that if you're messing with it, it doesn't update it. So let me just go here and just say, edit that. Get out of whatever you're doing, please. Okay, edit, please. I'm just going to go 1 volt, like a DC does. Okay, so let's look at it again. Okay, so the DC is not 1 volt. In fact, I didn't understand that at all. It didn't do anything. But as the general master of all stupid things you might possibly want to do, I've altered my diagram so that I'm showing an incorrect voltage. So this theme is constant. It is trivial to do this, and I don't mean doing it as a super stupid person, but sometimes you do it by accident. I've had different values for resistors caused by the simulator as displayed. I can readily do this by going into it. So as a general rule, how shall I put this? If you're doing the spice stuff, I think you'll find if you go into the simulator first and you enter the parameters that you need, it will work. If you go from the top down, your chances are a little bit more dodgy for things that you're taking like voltage, current sources, and that sort of stuff. For passives, they appear to be happy if you edit them from here, which is inside the spice model, or from the screen. They look like they get the same value more reliably. The models, you just have to do it in the model. So I think it's the sources where I've had the most problem with this. Beware, double check if you're having problems, okay? So enough about that. So while I'm on this thing, what are these 3 things here? Passive models, they're basically the resistor, capacitor, inductor. The model page is for subcircuits and transistors, which are called model statements. Sources are for things where you're actually dealing with simulation. So I'm generally sticking up here, and for this entire talk, I'm only dealing with these 2 values here. That's when you're doing like an AC analysis or a DC analysis. It would start here. Whenever you start doing transients, it has special tabs each for the various types of things to make it easier for you to fit the parameters. I'm a little unfamiliar with them. Didn't even bother to test them. You probably know what they are, but that's why they're there. They're to help you fill in all the parameters that are specific to a type of signal, and that's actually the voltage itself, not the simulation, right? Okay, so I will just pause for a second and see where I am in my talk, because I'm trying to be a little bit respectful today for change. Oh, I've got to take the slides so to start behaving. All right. Yeah, I think I've got to it. Okay, so I talked about this .spice init file. You're going to land that in your project directory. It's a safe place for it, and you only need it if you're using version 5. And in it, this is what you stick in. It could be a different value from that. You'll have to look it up in the ngSpice manual. But basically, that's for PSpice only. It's not LTSpice, for example. Okay, I mentioned the pin number reassignment. You only need to do that when you need to do that. It works. I've had it fail on me because Captain's stupid. I can find a way to make it not work. But generally, I don't like it because it loses the values right after you enter them, and I don't trust myself. Okay, that's fine. So when you're dealing with a big chip where it has lots of pins, you will be simulating and generally your simulation needs to have as many pins as you need to use for the simulation, if you would. Let me try that one again. Back to KiCad. If I were to place let me do a 741. That's one that doesn't have a problem. 4-1. Wait, 4-1. Okay. If you have an op amp that has only one op amp inside of it instead of a quad, this is about the only one where you can do a simulation from directly from the symbol without doing anything else. That's because you're going to use pin 1, you can use pin 2, pin 3, pin 7, pin 4, I think it is, and this pin here, which I can't make out. And you'll use the alternate key assignment to use them. These two guys, you'll put an X beside them and you're done. So what I think I'm saying is if you're using a quad op amp or a dual op amp or anything that has multiple things in it, you have more work to do before you can actually run a simulation. If you're just simulating for the fun of it and not actually forward engineering into a PCB board, then you could use the op amp from the PSpice and not even bother with this. So it really depends on what you're trying to do next. So if your job is to simulate and then after simulate, looks like it's working, work on the PCB board, then some of these symbols are going to need some work to get them to work with the models that you'll find. Oh yeah, I did mention that there's no models supplied, right? It's on one of my pages, but what you're going to have to do in, let's go here, is when you're doing a SPICE model, your SPICE model has to be on your disk. So you have to be able to find it, which means you have to download it. I've had trouble with libraries. Specifically, I find the transistor libraries that I borrow from LTSpice don't want to run under ngSpice. It gets confused for some reason. So what I have done in my examples is I've just pulled out the model that I want, dropped it in a file and used it. But when you're doing a SPICE model of, if you have a library full of like op amps, I have an example where that does work, so I'm going to suggest that libraries for subcircuits probably are okay. The problems I'm having center around my reuse of an LTSpice library that for some reason, I think it's ngSpice is balking at. It's probably not a KiCad problem, it's probably getting it the right information. Okay, but this is not a showstopper for people who don't have LTSpice. It could be a showstopper for you because a large number of the models you really want to use are already there. Because if you're using transistors or you're using or MOSFETs, whatever, you have no work to do. It's already there in LTSpice. You're almost never going to have a problem. Okay, this one does make you do some work. It's entirely possible to take the data from LTSpice, but you'd have to do work to do that, like find an automated means to separate the transistors into a directory so you can grab them and use them. That does work. I've not done it automated. I've done it manually, and of course, they work fine. Okay. Okay, so I probably missed buckets here. The slides. I'm using a freeware version of PowerPoint. It's not all that necessarily good. Okay, the data integrity problem showing the values shown in the schematic are separately stored from the values used by actual simulation. That's a showstopper for me. I can't trust that what I'm looking at on the screen is what's being simulated, and you're seeing very simple models. So for me, I would be concerned if running a simulation altered the values that I'm seeing, and I can prove that it does sometimes. It's the dial on the resistors will actually change the resistors sometimes and not tell you that it's changed them. Yeah, it doesn't display the pin node mapping, and sometimes it doesn't. I've experienced a couple of cases where I deliberately made a mistake and tried to correct it, and it wouldn't let me. And one of them was putting in a transistor whose pinout was backwards and then trying to remap it. I think what that is has to do with the order of steps, and I could have recovered it more easily than I did. I just noted it. So these are vaguely annoying if they happen to you once in a while. Of course, if you're not me, that probably is the case. If you're me, you'll see them every freaking time you try it. So I did make the attempt to take what's available in LT-Spice and just port it over by dropping the files in a directory. That didn't completely work, but I think it's just related to possibly models. I found it with BGGs. I haven't tried Mosfets or JFETs and that sort of stuff. But there's no problem in using LT-Spice data to get your models. It will run, and it's because PSpice is basically PSpice and Spice is basically Spice. There's hardly any difference. It's really hard to find a model that doesn't execute. In fact, I don't know why they're considered to be different flavors. I haven't run into it quite yet. But what I'm doing when I'm doing the modeling is I have set the simulation to be PSpice. I set it to be LT-Spice. I set it to both. I tried Spice. I didn't see any difference in the way the simulation ran. And that's because by and large, the models are compliant with all of them. And I think I'm done. So are there questions that I did? I heard one.
Go ahead, Peter.
Please. Peter. Yo. Sorry, did I just... I'm not hearing anything on my device.
I think maybe he's locked up.
Search, right, darn him. Probably a really important point.
He'll be back in a sec.
Okay. All right, so
Can you hear me?
Go ahead.
There you go.
Oh, can you hear me now?
Yeah.
Okay,
Yep.
good. All right. I said, first off, thanks very much for going through all this work on there, Wayne, because it's certainly you've satisfied my curiosity about how this simulator works. One quick comment on the using other models, LT-Spice model in particular. I've read on occasion where when they talk about using LT-Spice models in other spice flavors, sometimes it's just a very minor change in one of the lines of the model, and it'll work fine. Of course, what is that line? I'm not that experienced in that regard.
I've heard the same. I haven't seen it though.
The other thing is, let's assume for the moment that you're using KiCad for your PCB production, or laying out your PCBs. So but you had not done anything in simulator programs. Now that you've played around a little bit with the simulator program in KiCad, would you recommend directing your efforts towards KiCad simulator, or would you say go to LT-Spice?
I would say go to LT-Spice. I didn't want to. I talk about it a lot, but I'm not trying to sell it too hard here. It's much more powerful when it comes to representing the data than the KiCad simulator is presenting to you with. You've heard Dave talk about various ways that you can see things, little buttons you might click if you're in the Savvy. Those are unobtainium in KiCad as of today. They are available in LT-Spice if you learn them. Lots of things that LT-Spice can do. It's not a limitation of NG-Spice at all. It just happens to be that what's going on is KiCad's too new. If you're doing something pretty simple, an AC simulation, like I just did, because that's 90% of what I do is AC simulations and nothing else, it's fine. I assume the same of a simple transient, but if you're doing something complex, you might want to go back. Another criterion is how many models you have to put on the table. The most problems I have had is the voltages being 13 here and 0 in the part of the simulator where it's actually taking its data from. And so I get a simulation that just doesn't give me any values because it's I'm accidentally feeding it 0 volts. Or ngSpice kind of balks at the model for some reason, or the subcircuit for some reason, and it has to do with it shouldn't happen to you if your model passes if your schematic passes the syntax check, you know, the rules check.
Yeah.
Because that's checking for things like things left open and that sort of stuff. I've looked at voltages and see if they are sort of like required to be on the schematic by the time you get to the PCB. They don't seem to be relevant. And in point of fact, if you really wanted to do this, you'd probably have some physical things, because I've done this. Like you might have a pin header, and the voltages here are connected to a pin header, and the pin header connects to the circuit. And that sort of stuff. That might be more relevant to how you actually want the PCB to go. That all works. Okay.
Okay.
If you're using LTSpice, I would say start from there and then transfer it.
Right.
If you are in KiCad and you want to do a quick simulation, it might be quick.
Well, actually, that brings me to my last question, or at least I think it's going to be my last question. If you have a drawing already done in a schema and you wanted to simulate that, does that mean you have to redraw it in the simulator, or can you port it over?
Can't. You have to. Sorry, if you have a drawing in which simulator?
You've laid out your schematic in KiCad in this schema.
You do not have to. If you want to simulate it in KiCad, you don't have to draw it. If you want to simulate it in LTSpice, of course you do.
Oh yeah, no, I understand that. I'm just saying, so you don't have to duplicate your efforts.
Yeah, that is the selling point.
Yeah,
I'm going to say there's a little there's a fair amount of work to get the models to run. In my case, you remember I did that impressive looking quad op amp low pass filter thing for the DC radio. I would have had a lot of work to do to make those op amps run on LTSpice, because they are in fact quad op amps, and I have to actually write my own PSpice code to glue them together to get it ready so that ngSpice can consume it. That's not available in the Spice models themselves, and it's not available in KiCad. It's a file you have to write. So I assume there'll be a lot of that. But I got to tell you, the people that are using this, they love, first of all, you will not see a single complaint about this on the internet. When I was having my sorrows, I was looking hard, man. That people love this to death. Some of the people are new users who've never used something else, and they, I guess, get lucky by using the right. They followed the right guy or something like that. They get the job done, doing something simple. A lot of the users are significant Spice users who want to get their hands dirty, and it's easier to do that, I think, with ngSpice, because it's an engine that can be run standalone. You can actually, should have mentioned, if you go to the file thing, there's an export. You can export the netlist to a Spice editor and run it offline. And I'm thinking a lot of the power users do that because they're into making their own Spice models. So should you be heading in that direction, it's very worthwhile doing here. If you're doing anything, that's relatively simple, just transistors and simple op amps, it wouldn't be a big deal using KiCad.
Okay. All right. Thanks. Thanks for that, Wayne. And I think Dave had his hand up. I'm not sure.
Yeah, he did.
Okay.
Actually, Wayne answered my question. I was going to ask about, I was going to basically ask, similar to what Peter asked, when is a good time to use the KiCad Spice simulator, and you answered that. You answered it quite well about why you'd want to use this and the power of it. So I'm fine. I'm good.
If it's not obvious, you can. I thought when I started this thing that you wouldn't be able to kind of take any random model and put a simulator on it. It'll be there will be models that will be hard to do this with, but it's not clear black and white. This one will simulate, and you can do a KiCad PCB from it if you want a 1 transistor amplifier. but most of the things that I was considering at the time I was writing that comment to you at the beginning, I don't think they're real showstoppers. KiCad's sort of smart enough to get around it.
And I guess there's also the stubborn factor too. It's like what, remember, you guys are old enough to remember WordPerfect versus Word. Remember back in the day, everyone used to use WordPerfect. They loved it. And we got put a gun against our head to use MS Word. So part of that is some of us using LT Spice. We love it. We don't want change.
Well, it's what the devil you know.
I would say you possibly don't want to be an adopter right now. You might want to just sit on the fence long enough for them to stabilize some of the things I've been seeing. The main thing I'll point out is it's changing rapidly. The difference, there are differences between the 5.14 version I have downstairs and this version. Not a lot, but they're still changing it. And I think they're just easing their way through it. You have to understand their model is some of them are paid, but basically they do this off the side of their desk. If they're given the time to do it, that's great. Their priority is making the PCB generation optimal for the people who are the largest number of their audience. I guess the second priority is making the schematic editor a little bit more poppin', I guess. I don't think they have a lot of people sort of on the user experience around the simulator. Doesn't make sense to me. I mean, the problem is big as just look at the scale of the system. It's likely most of the resources are on the PCB and the schematic editor. So I'm saying that because it might take them a while. If you jump in now and you find stuff that's really a pain, you're going to learn to like it because it's going to be there for a while. If you wait a while, they might slow down. Like they might not actually go that fast, but they are making changes. I would say if you're sitting on the fence, and maybe we want to do a review once a year or every 2 years or something like that.
That's an excellent point, Wayne. Is that if you're, I think, and you echoed this. I'm going to echo exactly what you said. The power of this is if you're using this as a schematic editor, you've got your schematic, as what Peter was saying. You've got your schematic. Eventually, hopefully, you could just push a button and it simulates it and it tells you how it's going to perform. Wouldn't that be marvelous?
Yeah, I claim it's possible. Yeah, I was against it when I started this, but I think it can be. You will. I'm not covering all the things you might have to do to help you along that way. Like you will draw a different diagram. I think if you knew in advance that you were going to do a simulation, I think you'd probably lay things out a little differently because it'll make it easier for you to put the voltage supplies in certain places and that sort of stuff. But a little, okay, that's emphasis. You can make anything work, I'm sure.
Okay, excellent. Anybody else? Okay. Thanks, Wayne. That was good. That was good. Okay. We've got one other thing to discuss, and possibly if we've got a few minutes, I can do my ham radio bio. I was talking to Peter earlier today, and we're thinking about adding a new topic. It's going to be called shack gadgets, things that you use in your shack for testing on a regular basis. I know I've got one. I use it not a heck of a lot, but I use it quite often. So I could do something with that in another meeting. So if you guys have anything that you want to contribute to that topic, just let Pete know, and we'll try and fit you in on the schedule. Okay, I guess I'll do my... Yeah.
Why don't you save that for the next meeting? Save your bio, because I'm going to have to run in a couple of minutes.
Yep.
So I'd like to hear it for number one. So, why don't we save that instead of you rushing it through now? why don't you save it for a subsequent meeting, and that way you can we'll have more time to
Okay.
do that.
We'll have to do it in next month's mid meeting. The
Oh, you're not. Oh, okay. Sorry, you're not around.
no, I'm the next mixer. I'm going to be doing the DCR, our latest version.
Okay.
And that's probably going to take half an hour, 45 minutes. So I can do my my bio in the next mid-month meeting.
I'll put it all down the schedule there. We'll see how it fits. We'll be surprised what we can fit in.
Yeah. Okay. Alrighty. Does anybody else have anything they want to talk about or bring up, or any questions? No, I guess we're good. Alrighty, folks.
Is the buildathon still in the plan? Or?
Yes.
When is it happening?
We don't. I haven't scheduled anything yet. I got to talk amongst the folks here.
Okay.
How we're gonna do it. It's not quite at the step of putting a kit together. We still I got one glitch I got to work out, but basically it's working with it works quite well with the PARC HB, and I have it also working with a analog VFO.
Okay. All right. Thank you.
Yeah, I'll when I do present the DCR, I got a couple of videos I recorded using the HB and the analog VFOs.
Okay. Sounds good.
Alrighty.